All right, it is about 2 o'clock, so we will go ahead and get started. Thank you all for joining us. We have a great group here today. I'm Candace Shively with Utah State University Extension and the Center for Water Efficient Landscaping. And these monthly webinars are supported by USU and USU Center for Water Efficient Landscaping. Today, we're fortunate to have Grant Cardon joining us, also from Utah State University. Grant has been our Extension Soil Specialist for the past 15 years, and he is a great educator and great speaker, so you guys are in for a treat. Today, he's going to be covering how organic matter and living organisms work together to improve the water holding capacity of your landscape, garden, and farm. So if you have any questions, there is a Q&A box, and there's also a chat box. If you could use the Q&A box, that helps me keep track of questions as we go along, and we'll do our best to get those answered. And with that, I will turn the time over to Grant.
Great. So do you need me to share a screen now at this point?
Yeah, you are welcome to share.
All right. Is everybody seeing that now?
Looks good.
All right. Well, it's great to be with you all. I'm looking forward to it. This is the first time I've done one of these webinars for CWEL, so bear with me if you're expecting something else, but I like to talk about soils in general a lot of times to establish a foundation as we go along, and then talk about those things that are going to really affect the topic, in this case, soil-water-plant relations. So as we get going on here, we're going to talk a little bit about basic soils and what is soil health in the first place, and then branch into some of the properties that we can actually manipulate to advantage and in optimizing these soil-water-plant relations. So hang on just a second. There we go. So the first thing I want to talk about is what is soil health. You often hear the term soil health or soil quality kind of used interchangeably quite often. Soil quality is kind of where this discussion over decades ago really kind of started, and it's morphed more into the idea of health. As you think about the word health, the reason we've kind of shifted to that idea is that it has something to do with something living. Quality was kind of disconnected from life in a lot of ways. But soils are literally living, breathing tissues, and we have to account for the living fraction and the non-living fraction when we're talking about managing these to optimal effect for plant growth and for protecting the resource and having the resource function as it should. Soil health then is kind of defined really as the quality or health of the soil, its fitness, in other words, in supporting plant growth without resulting in any kind of degradation to either the soil itself or to the surrounding environment. And in some form or another, this is the definition that you'll see that's used in describing soil health. And when we think about it, we kind of have a mind's eye view of what soil health is. We would think of something like this as not being where we would look at maybe something like this as being a healthy, productive system and so forth. But, as we contrast those two things, there's a lot that's going on behind the scenes and underneath the soil surface that may or may not be healthy in either of those two situations I just put the pictures up there for. And so we want to go back and really kind of look at just some basic soil principles and properties and how they work together to make this a good functioning system that supports plant growth and maintains the life and health of the soil as well. So let's just go back and take a look at some basic soil science. All soils, no matter where we find them in the environment, come from some original parent material, a rock or the material that settles into a given location, and that then begins to accumulate at the soil surface, as you can see represented here right at the surface of this particular picture. That material, as it accumulates over time, gets to interact with a number of different what we call soil forming factors. The topography of the area as it accumulates soils to different depths depending on the steepness of the slope or the valley bottom, etc. The climate that works on of that material, the wetting and drying cycles and so forth that might affect the weathering of the material and the breakdown of the material and things over time. And then it interacts with a huge amount of living material, organisms, plants, and so forth, to give it a great deal of character. And we're going to talk a lot about that particular fraction as we talk about soil health as we go along. Then you have the parent material itself, and of course, it can work over time. All of these things work over time to produce what we call a soil. If we take a look at any given volume of soil, a couple of key things about the properties of them become evident. First of all, fully half of that volume is pore space, and it can be filled with water or air depending on the conditions that are there. But this is a vast reservoir for the exchange of both gases from and to the soil, as well as water that's stored in there. And of course, water is the all-important factor in supporting plant life and the living fraction of the soil as we go along. But it depends upon the other half of that volume, which is the solid material in that soil. Most of that is the mineral material that comes from the original parent material that soil developed from, with a little bit of organic matter mixed in. Now that organic matter, even though it's a small fraction of the total solid material, is really what ties the whole bundle together in ways that allow it to function as a plant growth medium, and will help over time both maintain and improve the health of the system. So we're going to look at how these things interact as we go along, and how we might manipulate them to advantage. The first thing we'll take a look at is the mineral fraction of the soil there. And of course, when we're talking about that, we're talking about the sand, the silt, the clay, those kinds of things that develop from the minerals in the original parent material, or that come about as ions and elements dissolve out and recombine into new minerals in the soil themselves. So we can look at the sands and the silts and the clay, and we have kind of an intuitive idea, having grown up playing with this stuff and getting it on us as we've been out in nature and things like that, that sands are larger than silts, which are very much larger than the clay particles in the system. And they each have a different feel, tactile feel to us. Sands, of course, are gritty to our touch. Silts, when we wet up a soil and rub it between our fingers, are smooth, but they're not sticky. Clays, on the other hand, when we rub them between our fingers, are smooth, but then when we pull them apart, we get the stickiness that is associated with the clay particles. One of the things we talk about when we talk about texture is the relative proportion of those three mineral components in the soil. But there's a couple of important things that we want to know aside from the size of the particles in the mix. The first thing is that the sands and the silts are pieces of the original mineral material that came from the parent rock or sand or other thing that settled in that area and began to become the soil. Inside this fraction of the sand and the silt, we'll find the very same minerals that we found in the original parent rock. So we'd find quartz and feldspar and mica and other minerals that we would have found in the original rock. Clay is also a size, as we've noted before, of a particle, but these are new minerals that develop in soils over time as elements and things dissolve out of the sand and the silt and the rock and the organic materials that are there and recombine into new minerals. And when they do, they form these little flakes, literally, of a new crystal. And so they look very different than the sands and the silts, which are spherical in shape. These clay minerals, excuse me, I'm going the wrong way. These clay minerals are literally little flakes of new crystal that develop in soils. So they look like a little crystal, or we'd call them like a soil snowflake, more or less. They're hexagonal in structure, and they're very much broader across than they are thick. And so these clay particles contribute pound for pound far, far more surface area to our soils than do the sands and the silts in that fraction. And that's an important aspect of clays, and it contributes a lot to the character of our soil. And we'll see why that's the case as we go along. As we said, clay particles form in place in soils over time. And so they're forming in disturbed environments. They're forming in imperfect conditions, not controlled conditions. And so when they do form, sometimes things go missing in the structure. And when that happens, it gives rise to unsatisfied charge within the clay particle itself. Most of the time, what's missing in a clay particle is a positively charged element. And so we're left with a great deal of unsatisfied negative charge on the surfaces of the clays. That is not the case with sands and silts. They have very little charge on their surface. But this is a really nice feature of clays, because then positively charged elements that are in soil solutions can stick to the surface of the clay, and they can be retained there with this little magnetic attraction that stores those ions in place against the flow of gravity with water and so forth. And they're not washed out of the system. They're retained in the system on the surface of the clay. Conveniently, I suppose, most of our nutrient elements, things like magnesium and copper and zinc and iron and calcium and others, are positively charged ions in solution, and so they can stick to the surface of the clay and retained there for later use by the plants or animals in the system. So clays, because of this surface charge, have a lot to do with the overall nutrient retention in soils. If we take a look at water, water is an electrically balanced molecule. It's got just as much negative charge as positive charge. But the hydrogens, which are positively charged, like to stay on one side of the molecule and not visit the other side. And when that happens, we set up what we call a dipole, where we have two centers of a small positive charge on one side and a small negative charge on the other side. But this is really, really important in a natural system, in a soil system, because now water can also stick with this little electromagnetic attraction to the surface of the clay. And that water then can be retained in the soil against the flow of gravity, or the draw of gravity pulling water out of the system through the pore structure of the soil. And so clay has a lot to do with both nutrient retention and water retention. But if we look at soil textures, different mixes of sand and silt and clay in our soil matrix, we note that there's all kinds of different mixes that have different characteristics or different properties. Loams in the middle of the mix are those that have kind of a real optimal distribution of sand, silt, and clay in the solid fraction of the soil. So they have a lot of large pores and small pores, and a lot of reactive surface area that comes from the clay and so forth. And these are really the most, in terms of a plant growth medium, the condition which is kind of physically or naturally optimal. But you'll notice that around that loam category, there's all kinds of other named soil types that have loam in their name. So these have loamy properties that are also quite desirable for use in a plant supporting system. Because of clay's overwhelming properties compared to the sands and silts in the mix, it doesn't take a lot of clay to begin to have everything act like a clay. Clay's got the largest chunk of this particular graph, as you notice here. For instance, we can have a soil that's somewhere around 45–50% sand. We can follow that up here, and it gets above about 40% clay, and it doesn't matter how much sand is in the mix. The properties of the clay overwhelm things, and we end up having it act mostly like a clay. So if we think about things, we can get too much of a good thing. Clay is a good thing because of nutrient and water retention, but then there's aspects of that system that we'll have to manage in other ways sometimes in order for it to be productive. So let's talk about that a little bit. As we get more and more clay in the system, you'll notice that things like aeration potential goes down, drainage potential goes down, and compaction potential actually increases in those cases. water that's available to the uptake for uptake by plants actually increases as we get more clay because of that retention capacity. But we can get to the point where we have so much that it then begins to restrict the availability of water to the plants at higher clay contents. So we can't rely just on the mineral fraction of the soil, the inorganic fraction of the soil, to help us provide the best possible conditions for plant growth medium and the health of the system. People ask all the time, well, why don't we just add clay to a sand to improve its water retention capacity? Well, that does happen, but then we get this concomitant reduction in aeration potential, drainage potential, and increase in potential for compaction. So that's not the cure-all. We have to find something else that's going to help us improve conditions so that we get optimal performance, optimal soil-water plant relations out of the system. We accomplish that by treating our soils in a way that improves their overall desirable properties without introducing some of the negative things that can come as we've seen with increased clay or too much sand or those kinds of things in the system. And the best possible way of accomplishing that is inducing soil structure in our soils. Now, what do we mean by soil structure? Well, heretofore we've been talking just about the mineral fraction. Now we're going to introduce that organic matter that's in that soil solid mix as well. And we said even though there's very little of in the overall percentage of organic matter in the system, it's the combination of all of the mineral fraction with that little tiny fraction of organic matter that really makes all the difference. When organic matter begins to interact with soil particles, we get the formation in soils of secondary particles that we call aggregates. Now, these aren't clods. I can make clods just by smashing stuff together. But aggregates are formed by the intimate interaction of organic matter with the sand and the silt and the clay-sized particles. When that happens, it draws those particles together in units that then opens up planes of separation between the aggregates, and now we get larger pores that form in the system. We get area where aeration and infiltration can occur. We have areas where small roots and small animals and bacteria and fungi can explore the mix far easier than they might have otherwise. And so these aggregates are really, really important to the overall function, and we get quite a bit of enhancement in soil properties with that small fraction of organic matter working together with the mineral fraction in the soil. You've probably seen the structured soils, but you may not have recognized them as being an indicator of good soil quality or soil health in this case, and an overall improved development of that system. We've seen many cases where we have a very unstructured environment, and we recognize that immediately as being fairly undesirable. But it's important to note that we have within our power in managing soil systems the ability to increase or decrease dramatically soil structure formation and the development of soil aggregates and the maintenance of organic matter quantities in soils and so forth. I throw in slide up, it's a very busy slide, but I wanted to kind of just point out a couple of important things. Here we have just a chunk, a portion of a clay particle. You see this crystalline structure with different elements and so forth, and it has surface charge. It can interact with other things that have charges on them, and organic matter, as it turns out, has a huge amount of surface charge. All kinds of reactive sites in this organic complex organic molecule, this organic material in the soil, the humus and the humic and fulvic acids and so forth that accumulate over time. These also have charge on them, and they can stick to the surface of the clay, and they can bind things together. They can wrap around other soil particles and draw them in together. They can also hold on to things like micronutrients. You see that over here with iron being held in the area. And so organic matter has a lot of effect in bringing all these things together and also helping to store both water and nutrient in the system. And so we get benefits in any kind of soil that we apply or add or maintain organic matter levels in. We get improved drainage in high clay soils. We get improved water and nutrient retention in sandier soils, all soils for that matter. We reduce compaction potential. We open up those macropores and we strengthen the resilience of those aggregates that are formed there, and that helps relieve those kinds of things like compaction. We provide nutrients to plants as that organic matter breaks down and recycles nutrients back into the system for both plants and other living organisms in the system. And it improves the overall tilth and the workability and so forth of that system. So we get benefits regardless of what soil we put it in with this organic matter addition over time. And so one of the key features that you'll find in any description or discussion of soil health is finding ways that we can help maintain or amend soils with organic matter in different ways. So how does this all relate to soil health? Here's some facts that are really important about soil health, and you can begin to see how the properties of what I've described in both the soil particles and organic matter then kind of work in concert to produce these properties. We notice that the positive facets of soil health are the direct result of the interrelationship between the mineral particles and the organic matter, especially as it has to do with soil structure. These properties change very slowly due to natural processes. We just don't get, especially in our western US arid zone soils and other places throughout the country, a lot of natural input of organic matter that can accelerate the process of soil structure and soil health development. But we can affect it quite dramatically and rapidly in the negative way with human activity, negative or positive for that matter. We'll take a look at that as we go along. Management practices on our soils can have either a good or bad effect then, as I mentioned, with our human activity there. And balancing soil health in the end really means having a net positive effect on the overall condition of that system, that we don't see the loss of organic matter, we don't see the degradation of soil aggregation, and we don't see then the resultant increases in things like compaction and low aeration and low drainage and so forth. And an important aspect of that being then the diminished function of the living fraction, the organisms and so forth in that soil that rely on that system as well for their function and the cycling of nutrients and things like that in the soil, that they are important mediators of in the system. People that work with soils and experience a lot of these differences in soil health notice a couple of things when the system is healthy. Healthy soils are deeper and darker. And if you think about where that soil color comes from, it comes from that organic matter accumulation over time. They're easier to work. The aggregation and the structure allows that to be the case. They sponge up and they hold more water. We have a lot of reactive surfaces in organic matter and in clays then that are working together in concert to hold on to that water. They drain better because of the aggregation and structure. They're opened up more to both aeration and water movement in the system. The system breaks down organic debris that comes into the system far quicker when the soils are healthier, because the organic or the organisms in the soil that are responsible for that decomposition are actively transforming those materials much more rapidly than they would be if they weren't healthy and thriving in the system. Soils that are healthy have higher organic matter, less erosion because of stable structure. They're resilient to changes that might take place. And we see visibly a lot of organism activity in the soils. Earthworms in particular are a good indicator species. They're a macro species that we can easily see the evidence of, and they respond to the positive things in that soil system that all the other desirable organisms that help to maintain this the cycling of nutrients and the living function of the soil. Earthworms respond positively to all those same things. And so if we see good activity of earthworms, it's a good indicator that we're on the right trajectory in our systems. They also have a sweet, fresh smell. Now, I put the note here, I'm a dirt guy, and I get excited about things that maybe other people don't, but soils do that are healthy have this rich, earthy smell that quite enlivening as you get a chance to work with it and so forth. We're going to skip through a lot of these things pretty quickly, but you'll notice that they also have benefits to not only the soil, but other aspects of its management. Input costs are lower, we like less fertilizer in these healthy systems. Crop yields are typically higher and more consistent. Sometimes even the consistency of yield is more important even than high yielding systems. Greater variety of different both plants and organisms in the system, which help reduce the pressure of maybe some resistant varieties of weeds and other things, or non-beneficial organisms that can cause disease and so forth in the system as well. So we want more diversity as we go along, and that's the case in healthier systems. And we get better crop quality overall. The nutritional value, the marketability of them and all, because of the control of diseases and other things that might be in the system. So how does this affect you and me? The NRCS, that's the Natural Resources Conservation Service of the USDA, here back in 2016, established the Soil Health Division, where they're looking at all kinds of ways of both developing and promoting healthy soils and testing for and monitoring the progress of that promotion, those promotional efforts in building soil health. And so they're producing a lot of educational materials, a lot of guidance on both management and measurement, so that we can begin to inventory and monitor soil health across the country, across the world for that matter, as this campaign for soil health is actually branched out across the world. Eventually, the idea is there to establish, as we do with things like our own water quality and air quality and those kinds of things that are so important to us, some kind of resource accountability mechanism for the enhancement and protection of soil health as well. So what can you do? The things that reduce soil health are the things we got to watch out for in the way we manage our system. If you're talking about what a healthy soil is, it really hinges upon good organic matter maintenance and good soil structure building and resilience over time in these systems. And that's a concert of actions that's going on with the living fraction, the organisms, as well as the organic matter, as well as the mineral matter in the system. And so if we look at the things that negatively affect that in particular, then those are the things we have to watch out for in managing our soils. The first one, obviously, is erosion and the loss of soil materials, the destruction of aggregates in a way that allows soil particles to either flow or wash away or blow away in systems, which then is an indicator that we've begun to destroy soil structure and we're not protecting or conserving that soil resource in place. The loss of organic matter, obviously, is a major issue in reducing soil health. We have to be putting organic matter back into the system quite frequently in order to maintain it and increase the organic matter levels. And so there are management aspects of that we can then enhance, either adding it directly and incorporating it in soils, or using plants and other mechanisms of putting organic matter into the soil system. And we'll talk a little bit about that with reference to cover crops here soon. We have to then look at soil structure breakdown. That comes as organic matter loss happens over time. If we're not putting that back in, the microbes are going to continue to break it down. If they're breaking down organic matter that's involved in soil structure development, then we'll see a decrease of that over time as well. We can have other things, physical things like compaction, mechanical breakdown with excessive tillage, and what have you there that cause that to happen as well. The soil structure, of course, we've talked about its importance in aeration, infiltration, and what have you. So we get kind of a spiral of things that begin to happen as we mismanage soils in a way that promotes soil erosion, the breakdown and loss of that soil organic matter. Then aggregates begin to break down. We get compaction, we get additional loss of organic matter and so forth, and this continues to spiral. So anything that we can do initially to protect against soil erosion and the loss of organic matter and soil aggregate or structure breakdown, then we're going to be able to maintain and then build upon that system in order to enhance not only soil health, but then its overall optimal function in terms of soil-water-plant relations. So how fast, does things like this take place in terms of establishing? This isn't a quick fix kind of thing where we add organic matter and we see a rapid response in soil structure development. This takes time, and so it takes a dedicated, persistent effort to make sure that we're increasing organic matter over time to build soil structure. It takes about 4.5 years or so in Western US soils to begin to build optimal soil structure up. But it takes very little time, about 0.2 years or just a couple of months, to begin to destroy soil structure if we discontinue the addition of organic matter in a system or do something physical that's going to begin to break down the aggregates. So we can have a very rapid negative effect, but don't think that this is going to be something that you can quickly change in the system. It's going to take some persistent, dedicated effort to make sure that we're building and maintaining organic matter levels so that we protect these soil resources. We want to make sure that we put in organic matter additions whenever possible. And just keep in mind, we cannot overcome the lack of organic matter in our soils with the addition, continued addition of mineral fertilizer inputs. In the long run, that organic matter, which is so important to aggregation, so important to soil organism function, feeding them and providing an environment in which they can thrive, we lose that functionality in the system with the loss of organic matter over time, and we just can't recover it by continuing to put additional mineral nutrients into the system. Soil salinity also reduces the overall soil health if we get the buildup of excess fertilizers that are beyond what the plant needs. Those are mineral salts of the nutrient elements. They can begin to build up. We can get problems with the uptake of water from the system because of the amount of salt in the system. And we can also get the destruction of soil structure, particularly if we have sodium-based salts. Sodium-based salts get in between the clay particles. They start pushing things apart, and they disperse the system, which it notes here, in a way that causes those soil aggregates to begin to break down, and then we get the problem with crust formation, the plugging of pores, and so forth. So soil salinity often results in from excess water and fertilizer in the system. We get a restriction of water uptake. Sodium salts, as we mentioned, can cause dispersion. We have to look at making sure we have the right plants growing in a saltier soil, and then do some careful cleanup to get those salt ions washed out or leached out where possible. Other things that reduce soil health are things like soil contamination, where we have a buildup of non-target effects of pesticides and other things that we might bring in to the system that we need to pay attention to, because as we apply those, and they may be helpful in controlling weeds or pests or disease or other things, if we mismanage those and we get them into the system where they can leach to groundwaters or run off to surface waters or other things, they can have significant non-target effects, which reduce both soil health and the overall fitness of the environment. So our best method for those kinds of things is to make sure we're only using those chemicals when and where they're needed and in the amounts that they're properly needed. We need to rotate our crops so that we don't get buildup of disease vectors in the soil and other things over time. As we rotate into other types of crops and areas, we can greatly reduce the pressure of those disease vectors. And that's a non-chemical way of making sure that we control that. I mentioned here the aspect of cover crops. Cover crops are another important thing that we haven't talked about a lot yet. But cover crops are one of the key ways that's promoted by the USDA in building soil organic matter over time, where we're keeping our soils from being unprotected at any moment without a growing plant in the system. The idea then is to protect the soil surface from erosion. It's to, with the root system, add additional organic matter to the system over time that might not have been available to us if we leave those soils dormant or open. That continues to then feed the organisms with that organic material, root exudates and other things in the system. It can draw up excess nutrients, which can become salt buildups over time, which helps reduce that impact as well. And so cover crops have a lot of advantage in areas where there's ample water to support them, so that we can continue to grow a plant that's maybe not our desirable crop cut in a garden, but then continues to provide additional organic matter and protection of the soil system. There was one question that was posed earlier about the use of cover crops in dryland systems where we don't have a lot of water available to us. And those are very important areas that we have some projects here at Utah State University looking at to see if we can do a better job of maintaining organic matter accumulation in dryland systems where we have very little water available to us. But we rely mostly in the state of Utah in irrigated settings on work that has been done in other areas on cover crops. And you can get a great deal of information on that at the USDA's Soil Health Division website, where they talk about various mixes and other things that are useful in a number of different settings, whether it be in the home garden or small farms or larger scale farm systems. So the role of cover crops in that case is then to protect soil surface from erosion, add organic matter to soil systems, which then helps retain water, build structure, and so forth, as we've discussed. And important, really, in a key way, is the promotion and maintenance of microbial activity and diversity in those systems. It reduces weed growth in establishment, reduces the need for then chemical use to take care of that, where competition can largely benefit us in weed control and what have you in the system. So the bottom line, and I know I'm kind of up against time here and want to save time maybe for some questions, is that we just don't treat our soils like dirt. That's a kind of a cute way of describing it, but the idea is to build soil and be active in the process of building soil and make sure that we're putting enough organic matter back into the system, whether it be amending the soil with organic materials over time, or looking at the opportunities for cover crop establishment and use so that we're putting organic matter back in the system, and then making sure that we don't do anything with our management in those systems that's going to cause the destruction of soil aggregates, that's going to cause the exposure of the soil surface to erosional effects that can also reduce soil structure and performance, and that we're feeding those microbes. We don't forget the living fraction of the soil, which is so important to the creation of soil aggregates, to the cycling of nutrients as those microbes mediate the breakdown and decomposition of those materials and the cycling of them over time. So with that, I'll take...
we will wrap this up. And Grant, thank you. I really appreciate it.
That's all right. Great to have been with you.
All right. See you guys.
See ya.